Hi everyone, I'm Amelia. I'm a master's student with Michael and Sizzle. And today I'll be talking about policy gradient estimation. But first, Friday at 5 p.m., what is happening? Yes. So for your proposal, the most important thing is that the project you want to work on is a sequential decision problem. If you're unsure on any of those components, please come by office hours or post on Ed. We're happy to clarify. With uncertainty. Don't forget that. Come by office hours if you're not sure. We're happy to help talk through it. And also as a note, it's totally fine if you don't yet know how you're going to solve that problem. But you need to make sure that the problem you're interested in solving has those characteristics. All right, and with that, we will get started with policy gradient estimation. So, like Josh talked about in the last lecture, we have some policy pi, and pi is going to tell us what action to take based on the state that we're in. So for this lecture, I'm going to be using the example of having a policy to control the temperature in a building, and we're going to say that the actions that we could take would be turning on the heat or turning on the AC, and then we'll additionally have the constraint that we're never doing both at the same time, just because that pretty clearly seems like that wouldn't be a great policy based on our expert intuition. So one thing that policy might look like is for every possible temperature, we have some associated action. So we could say at 30 degrees, we're going to turn on the heat, and at 31, we'll also have heat. And then at some point, things get warm enough, maybe at like 85, now we're going to turn on the AC. And as you can imagine, in cases where we have large or even continuous state spaces, storing a policy like this wouldn't be possible. So that is why we're going to be looking at policies that are parameterized, and we're going to call the parameters theta. So to give you an example of what that might look like for this case, along this axis, we're going to put possible temperatures. We'll say 0 to 100 for these purposes. The weather here is pretty nice. And then rather than storing a table with 100 different values, we could set, for example, two parameters, maybe theta1 and theta2. And what we'll do, our policy based on these parameters, will be that if we're below theta1, we turn on the heat. And then if we're above theta2, we turn on the AC. And between them, we have neither. So once we have this policy that's parameterized, the thing that we're generally interested in optimizing, which will be Kiana's half of the lecture, is the utility of it. And we write the utility of the policy parameterized by theta as u of theta. So in our optimization, many of the methods rely on the gradient of u of theta, and that's why we're going to be looking at a few different options for estimating that in this lecture. So because theta will generally be multiple variables, otherwise we'd have a very simple policy, gradient u of theta is going to have this form. So for every theta I, we're going to have a partial derivative. And let's say that we have n of these parameters theta. For the example that I just showed you, n would be 2, and this is going to give us an n by 1 vector. And before I go on, I wanted to make a note. This portion of the lecture, and also probably your portion too, is pretty calculus heavy, and depending on your background, you may have done that more or less recently. So I don't want you to feel like calculus-related questions are less legitimate than questions about material that maybe you've only seen in this course. I definitely had to look up stuff preparing for this, and if the calculus is a sticking point, please say something. We want you to feel good about every step that we're taking. So the first method is something that you probably saw in early calculus, and that's going to be finite differences. So in finite differences, we have some function and then some point where we're interested in computing the derivative. And does anyone remember what we do for this method? No worries. So we're going to take another point some small distance away that we call delta, and we're going to compute the slope between those two. So the dotted line is the thing that we're computing, or the dotted line is the thing that we're estimating. The non-dotted line is the thing that we're computing. And we're using that to get a basic approximation just around that one point of interest. So in the multivariable case that we're considering for the gradient of u of theta, this is going to look something like u of theta plus delta E1 minus u of theta all over delta. And then we're going to do one of these for each of our parameters theta. So you might be wondering what this E here is. This is a standard basis vector, and this index indicates the position at which we have a 1. All other positions are going to be 0. So here we would have a 1, followed by n minus 1 zeros, and so on. And the reason that we're doing that is that we're only applying this difference delta to one parameter at a time. And so this is going to give us an n by 1 vector with a simple estimate of the gradient of u of theta around some point. Does anyone have questions here? How do we feel about the first one? Yes?
What's u again?
Great question. U is the utility of theta, and we get u of theta, as Josh mentioned previously, by using rollout simulations. So this is something that can impact this method, is that depending on the variance of u of theta, it may take a lot of rollouts to get a good estimate. And the book talks about some techniques that you could practically use to mitigate the potential invariance between when you're computing this and then running the policy. Yes?
The data here are the parameters for the parameterization. I guess like for high dimensional case, will this first order approximation always work?
Oh.
You want to repeat the question?
So the question is, for the higher dimensional case where we have a lot of thetas, would this first order approximation always work? Kind of depends on the data that you're working with. We will get into more complex methods that are a bit more robust, but you can imagine like if the theta parameters are on very different scales, then you may run into issues applying the same difference to all of them. So this would be ideal for a simpler case, and some of the other methods would be better for cases like what you're talking about. All right, anything else? Cool, okay. So the next method that we're going to talk about is called the regression gradient. And this may have come up in other ML classes that you've taken, but when we do a regression, we have some set of data points, and then we're finding the line that best fits them. So this is that regression, and what we're going to talk about is what the line is that we're fitting. So we know that the thing that we're interested in is that we want to find the gradient of u of theta. around some point theta, we're estimating what this line would be. So the first thing that we're going to do is we're going to collect data points, and then we'll fit our regression line. So what should the data points be? We're interested in theta, and we want to collect a bunch of points, let's say. This is where theta is. And we want to collect points around it in its neighborhood, which we can find the gradient at. So we're going to create this matrix that we'll call delta theta. And we're doing a perturbation for each of our parameters. And this is going to be m by n, where m is the number of perturbations, and n, again, is the number of parameters. There's no right or wrong answer for choosing the number of perturbations to do. Empirically, a rule of thumb is to have double perturbations, double that number of parameters be the number of perturbations, but that could be based on computational constraints or expert knowledge, or you tried a few things and this was what worked the best. And then the way that we get the perturbations is also something, there's no one analytical option that's the best, but empirically we find that randomly sampling from the normal distribution works well, and these are also going to be normalized random samples. So you can visualize that as though we have a sphere and we're sampling points along the surface. And so those would be what the perturbations are. So that's how we get our changes in theta. Yes, question?
Just wondering, if you're randomly sampling around that point theta, how are you getting a line from that?
Yeah, great question. So the question is, if you're randomly sampling around the point theta, where does the line come from? So once we have our random samples, which are the differences from the original theta, we also need to find differences from the original u of theta. And then I'll talk about the method that we use for fitting the line between the two. But basically, we collect both of those data points and then use the method that we would use for regression. Like, I think this also came up in the policy, or no, the approximate value function chapter as well. Yes, but that's a great point. That is what we need to do next. Any other questions? Yes?
Sorry, could you explain that sampling on the sphere that you just mentioned?
Yeah, so let's see. I'll draw a picture, and hopefully this helps, but if not, let me know. So we have some normal distribution. So we're sampling from some normal distribution, and we could have any mean mu here. And then we're using the samples from that distribution to perturb it. But when we normalize, then they'll all be distances of 1 from the original value. So we're just, like, we could be moving a distance of 1 in different directions for each of the parameters, but we're not going to be moving like 5 and then 3. So it's just constraining it a bit. Yes?
Would we be sampling from the normal distribution for each coordinate?
Would we be sampling from the normal distribution for each coordinate? We're applying the same perturbation for each coordinate, or the same set of perturbations. So we're not doing, like, we only look at this point for one of them. We would choose some number of points and apply that to all of them, which is what gives the m by n.
In n dimensions, you're sampling from an n-dimensional multivariable.
Yes. Yeah. Yes.
Are those random points what we call perturbations?
Are the random points themselves what we would call perturbations? So the perturbation the points are how we're perturbing theta. So the perturbation is like, okay, we've taken a point, this is how much we're going to change theta, and then we apply that change. And I think once we've applied that change, that's what we'd call the perturbation. Yeah. Any other questions? Cool, okay. So that would be how we get our data set of points for theta, and that's definitely the more complicated part of building this data set. And then when it comes to computing delta U, this is going to be more similar to what we've seen before. So using rollouts, like with Monte Carlo simulation, we're going to find U of theta plus delta theta 1 minus U of theta, and then we're going to find this difference for each of our n parameters. C of theta plus delta theta. And this will be m by 1. And again, these are coming from policy rollouts. So does everyone feel good on where delta theta and delta U come from? All right. So now that we have delta theta and delta U, we need to fit the line between them to estimate the gradient. So we're going to say gradient U of theta is approximately equal to delta theta, this upside down t means pseudo inverse delta U. And the reason that we're doing the pseudo inverse instead of the regular inverse is that we're not guaranteed that delta theta is invertible, because m and n ideally should be different, so it's not going to be square. And so when we do a pseudo inverse, like if we were doing the pseudo inverse of x, what this actually is going to work out to is the inverse of x transpose x times x transpose. And supposing that x is m by n, then x transpose will be n by m. And we can see that we'll be taking the inverse of something n by n, which is square. So that's what the pseudo-inverse allows us to do, and this is the same as what we used for approximate value functions, if you want to take a look at that in more detail. The 229 notes, which are available online, also go into this in great depth, and I recommend that as well. Any other questions here? Yes? Why delta? Oh, good question. So in this case, it's m by 1 because we're doing one of these differences for each perturbation. So in the previous method, we just did one difference per parameter, and that was n by 1. And then here, we're doing one per perturbation, so it's m by 1 now. And the important thing is just that we have an equal number of perturbations of theta and of u. And in the previous one, we just did one for each parameter, theta, so that's how we made sure those were the same in that case.
So would you do this for every single theta?
No, you don't have to do this for every single theta, since the perturbations are being sampled from an n-dimensional normal distribution. So we're moving all of the parameters in each perturbation, and then we're doing that m times. Yes. Any other questions here? Cool, okay. So the last method that we're going to look at is the likelihood ratio. And this is definitely the most calculus-heavy component of this lecture. So I'll try to go through it slowly line by line, and if any line isn't feeling good for you all, just let me know and we can pause there. So as previously, the thing that we want to compute is the gradient of u of theta. And the way that we're going to do that in this case is that we're going to use an analytical form of u of theta, which says u of theta is the integral over all possible trajectories of p theta of tau, r of tau, d tau. And I'll go through what each of the things in this integral is. So first, tau is going to be some trajectory, which is a sequence of states and actions. So for example, for our temperature setting, we could have a tau look something like this, maybe 30 degrees, and we turn on the heat, and then it gets really hot. 90 degrees, we turn on the AC. And then we have apparently a super powerful heater in AC, so now it's back down to 40 degrees, and we turn the heat on again. So that's one example of what a trajectory might be. R of tau is going to be the return for that trajectory. And we say return rather than reward because we're not just looking at the reward for the immediate state. We can use whatever type of formulation we want to have a discount over the entire sequence in tau. Generally, we'll be using the Bellman optimality equation, Michael's favorite equation in this class, but that's up to you if you choose to do that some different way. So we have the return for that trajectory, and then this term is going to be the likelihood of the trajectory as determined by the policy parameterized by theta. So, intuitively, what does that mean? Our policy is telling us, based on a state, what action we should take. So let's say that we have some policy where we're heavily prioritizing being super energy efficient. And so we're going to say theta 1 is like 10. And we're only going to turn the heat on if it's below 10 degrees. And then theta 2 is 95. And we only have the AC on above 95 degrees. So if we had a policy parameterized like that, then this trajectory that I just showed you would be it would be impossible. That would never happen, since according to these parameters, we wouldn't turn on the heat in AC. So the policy is determining how likely a trajectory is. Do we feel good on that? Yes?
I thought we were trying to find the policy. Or do we already know the policy? We're just like...
We have some initial policy, and then we're optimizing theta that's parameterizing that policy by optimizing the utility of those thetas. So maybe an example that is more familiar is that if we have some neural network with parameters theta, then we're going to be optimizing for the best parameters of our neural network by finding the gradient of the loss. Yeah, we're trying to make sure that we're improving the utility incrementally, and the way that we're doing that is by finding the gradient of the utility and then trying to move our theta in a way that's positive for the gradient of the utility.
Thank you.
No problem. That was a good question. Anything else? Cool. Okay. So the policy that we have is determining the likelihood. And so what we're going to do is we're going to take this analytical expression and we're going to get an expression for the gradient of u of theta from it. And to start, we're just going to take the gradient of both sides. So the first step that we'll take is we're just going to move the gradient inside of the integral. So and then the next thing that we're going to do is we're going to multiply what we have inside of this integral by 1. And the reason that we're doing this is that once we've done that multiplication, now we can write these out in a way that allows us to simplify. So we're going to write this as p theta of tau times the gradient of p theta of tau over p theta of tau r of tau d tau. And you'll see that when written in this way, the expression that we have is actually taking the form of an expectation. So now we can write this as the expectation over tau of gradient theta, p theta of tau over p theta of tau, r of tau. And I'm going to pause here for a second. Does everyone feel good on why we can convert that to an expectation? Yeah, definitely. So let's see. I'll give an example. Let's say that we have f of x, then the expectation of f of x is the integral over all possible x, p of x, f of x, dx. And so we can map that form onto here where this would be the probability, and then this would be f of tau. P of tau, f of tau, and then we can write that as the expectation over this f of tau. Okay, sweet. So based on a trick in chapter 10.5 that I will not be deriving today, but I will note here in case you are interested. This is called the log derivative trick, and that allows us to write the expectation in this form. So now we have an expression for the gradient u of theta in the form of this expectation. Do we feel good on that relationship? All right, so we're assuming that we have some formulation for the return that we know that's simple to compute. So we're not going to worry about that part. And then the last thing that we need to do in order to estimate the gradient from this method is we need to find this right here. We're interested in the gradient with respect to theta of the log of p theta of tau. And there are going to be two different cases for this, depending on the type of policy that we have parameterized by theta. So we could have either a stochastic policy or we could have a deterministic policy. So when we have a deterministic policy, we have our policy parameterized by theta, pi theta, and every time we give it the same state s, it's going to return the same action A. So for example, every time it's 30 degrees, we say, turn on the heat. That's always what's going to happen according to this policy. By contrast, with a stochastic policy, pi theta of our state S is going to give us a distribution over actions. So maybe if S is 30 degrees, then in this distribution, 90% of the time we're turning on the heat, 5% of the time we're turning on the AC, 5% of the time we have neither. And this allows us to write pi theta for a specific action, like turning on the heat, given the state, 30 degrees, as the probability of taking action A from state S. So in the example I just said, for the action turning on the heat, when our state is 30 degrees, the probability is 90%. How do we feel about deterministic versus stochastic policies? Cool, okay, great. So during lecture, we're only going to talk about the stochastic case, and this may or may not be surprising, but it's actually easier to compute, and it's kind of interesting to see why. So for a stochastic policy, we're going to be finding the gradient with respect to theta log p theta of tau. And we're going to do each of these one at a time. So first, we have some tau. And in this case, we'll have it be a sequence where we have states, actions, and rewards or returns up to some time horizon. We could set that however we want based on compute constraints, knowledge about the problem, etc. In this case, I'm going to say we're only going to account for the last 10 steps. So p theta of tau is going to be the probability of our initial state. And this doesn't come from the policy. You'll have some distribution over initial states. That could be a uniform distribution. Again, it could be based on some knowledge about the problem. But we're sampling from that distribution independent of the policy. The policy doesn't affect where we're starting. So we have that, and then we're multiplying that by the product across our timestamps of the transition probability. So how likely is it that we go to the next state, given that we're in our current state, and we took this chosen action in our trajectory, and then we multiply that by the likelihood of that action according to our policy. So our policy says, for this state, how likely is this action? And then we say, based on our transition probabilities, given this state and this action, how likely is the next state in the trajectory? And this whole product gives us the likelihood of our trajectory tau according to our policy parameterized by theta. Does that make sense? Sorry, what did I say the last part? One more time. Yeah, definitely. Okay. So pi theta of the action given the state is the likelihood that we take that action from the state according to our policy. We're multiplying that by the transition probability that we get to the next state given that we were in our current state and we took the action that our policy told us, and then we're doing that product for every state in the sequence. And so that times the probability of our first state, which is not dependent on the policy, gives us the likelihood of the trajectory overall. Cool. All right. So.
We got a question.
Oh, yes.
Does that expression kind of follow from the chain rule?
Exactly. This follows from the chain rule. Nice. Yes.
Sorry, just underneath the pi in your product, what is that variable? Something's equal to 1.
Oh, that should be k. Let me write that a little bit more clearly.
And the superscripts on S's and A's.
Yes, the superscripts on the S's are the time that we're at. So it would be, S2 would be the second state in the trajectory. And I think actually, Michael, please correct me if I'm wrong, but I think this should be starting from 2, right? The product here? No, because we're going to 2 from 1.
On state 1.
Yes. All right. Yes.
So is it S to the K and then A to the...
Yeah, let me just clean up my handwriting
No.
quickly. That's my bad. Yes, that's K. Cool. All right. Any other questions here? All right. So the first part is done. We have an expression for p theta of tau, and now we're going to take the log of that. So the log of p theta of tau, and because we're taking the log of a product, we can convert this into a summation. So we have the log of the probability of our first state, and then we have, let me print instead of cursive. And then we have one last term in our summation. All right. So we've done the log. The product is a summation now. And then the last thing that we need to do is we need to take the gradient. And this is where having a stochastic policy actually is going to make things easier. So when we take the gradient with respect to theta of both sides, we will see that all of the, yes?
Should there be a log before the time?
Should there be a log? Yes, there should be a log before the time. Good catch. All right. So when we take the gradient of both sides, all of the terms that aren't dependent on our policy parameterized by theta drop out, right? So we can get rid of that, and we can get rid of that. And now the expression that we're left with is just this summation and this gives us another option for estimating. Yes? Ooh. Log. They dropped out because they didn't have any dependence on theta. So it's like if we were doing derivative with respect to x of y. Same thing here, yeah. Yeah. Anything else here? Any other steps that might not be clear? Yes?
Okay, this might be nitpicking, but should it be from k equals 1 to d minus 1, or should it be from k equals 1 to d?
Let's see. Good question. Not nitpicking. Yeah, that should be to d minus 1. Should it not?
I don't think so.
No.
We can take it offline though.
All right.
You want to find the gradient of the log likelihood over all of the state action pairs. And I think you have D of them.
Right, but if this term is, oh, right.
Oh, I see what you mean. Yeah.
Good catch. Yes.
Explaining why this is.
Oh, why we changed it to be depth minus 1? So, for example, in this case, where our depth is 10, we only know up to the 10th state in the trajectory. That's all we're remembering. So if we went to D, then here we would be looking at 11, which is something that we don't know because it's not in our current trajectory. So we're stopping at 10, which would be depth minus 1 plus 1 here. Yes?
But then we took the derivative over theta, wouldn't we end up with like not looking at the state, like the D state action pair?
When we take the derivative of theta, do we not end up looking at the D state action pair?
At that last term, remaining term, we won't be looking at pi theta of A given SD.
Yes, so the last term that we're left with would only be going to D minus 1 in this case, but Michael, should we assume that we know the trajectory beyond D, or?
Yeah, I think there's just a little tricky thing for the transition model because it goes to
Right.
D plus 1, but you know for the second summation, I think that can still go to D because you know what that is.
Yes.
So I think the peak theta trajectory should really be half like an extra term at the end, so that at the D level, the transition wouldn't matter because it doesn't matter the D plus 1 state. It just, we don't consider possibilities. We don't care what it goes to.
Yeah, stop pulling up.
Yeah. Anything else? All right. So that was the last method that I had, and you can see in the book, which also goes through the derivation for the deterministic policy case. And now I will let Kiana take over to talk about what we're going to do with these estimates. Oh, yes.
So if D is the depth, what's his K?
K is just the counter. That's the current stuff that we're looking at. Yeah.
So at D equals 0, K equals 1.
No, so K is stopping at D, so we would do K from 1 to D in this case. So first state in action, and then the second, and so on, all the way to D would be included in the summation. Yes?
We will be taking an expectational order to
up to the find this. But we only found this similarly, so would you go ahead and iterate over several different trajectories in practice?
Would you iterate over several different trajectories in order to find this?
In order to find the expectation of a trajectory.
Yes, in order to find the expectation, you need to consider multiple possible trajectories.
But, like, is it possible to look at each trajectory? Hard to find all of them.
Sorry, would you please repeat that? I'm having trouble hearing.
So, like, what I'm saying is, for the trajectories, in practice it might be hard to iterate over all of them. So,
Yes.
Something randomly or not.
Yeah, you would be sampling, and you can use different heuristics for how you want to sample trajectories. Some may be of more or less interest. Like maybe it's more important to have information about trajectories that we think are likely or high risk, etc. But you would need to be sampling. We would expect that in many cases you wouldn't be able to enumerate all of them. Yes?
I just wanted to understand from a high level, we did do was we're just trying to calculate the gradient of the utility function, and then there's like 3 different methods, like with finite differences, and there's the pseudo inverse, and then with this volume.
Yeah, so these are all different methods for estimating the gradient of the utility function so that we can optimize the parameters of our policy theta with respect to utility. So we're assuming we're not able to compute that gradient directly, and then these are some possible options. Yeah. All right. I will show you more about what we're going to do with this.